Okay, so we're going to finish up section 1.4 today. And to start with that, we're going to talk about the domain of a function. So if you're looking at a set of ordered pairs or a graph, the domain of a function is not that bad. We kind of did some of that on the first day, looking at a graph anyway. But if I give you an equation, it's a little harder to figure out the domain. So first of all, when you're doing your assignment for today, there's going to be a couple of questions where it just gives you an equation and wants to know if it represents a function. So for it to represent a function, if you solve for y and then graph it, that's one way to do it. But another way is to just think about what it is. You should have a good understanding of some parent functions. So you should know that if there's an x squared and a y squared, it's probably a circle or maybe a hyperbola or an ellipse, which you don't necessarily know what those are. But if x and y are both squared, then it's going to make some kind of shape that is not a function. If basically the general rule when you're looking at an equation is you can do whatever you want to the x and it's going to be a function. If you start messing with the y, that's when we create things that are not functions. And the only two things that really are going to make it not a function is if the y is raised to an even exponent or you're taking absolute value. So those are the two big things to look for in an equation if you want to just be able to look at it and know and not have to solve for y and figure out what the graph is. Okay, so back to what we're learning today, the domain of a function. And I have a handout in class, like I used to make everybody write it all down, but except for the little example pieces, the rest of that's typed up and you just glue a paper in. So if you weren't in class today, I'll give you that paper when you come back to class. Or you can just write it all down, whichever makes you happy. All right, so for the domain of a function, that's the set of all allowable x values, which we've discussed before. The key thing to remember is that for almost all functions, the domain is going to be all real numbers. But there are three reasons that we will not have all real numbers. We're only going to worry with two of them for now because we haven't talked about logarithms yet. And so when we do talk about logs, we'll talk about those domain restrictions in more detail. Okay, so there's three things that cause a domain issue and have to think about your domain. If it doesn't have one of those three things, then the domain is all real numbers. All right, so exception one, if we are creating a zero in the denominator. So if there is a variable in your denominator, there's going to be a domain issue. The problem is we can't divide by zero, so we have to take the denominator, set it equal to 0, and figure out what that particular x value is that's going to cause us trouble. So for this problem, if x is 3, then we have 2 over 0, which we can't do, that's undefined. So we need a way of saying that we want all numbers except for 3. So there's two ways that we can write that. We can use set notation, which literally says, these fancy brackets mean the set of numbers. X, this line means such that x is not 3. So this is just saying the set of x values such that x is not 3. That's saying any number except for 3 is good. In interval notation, you can say go from negative infinity to 3, but don't include 3. So we use a parenthesis, not a bracket. And then pick back up on the other side of 3 and go to infinity. And this little u, that's the union symbol. It means you're uniting those two groups, the numbers to the left of 3 and the numbers to the right of 3. All right, so I don't need you to write both ways. I just need you to pick your favorite way to write it and to recognize those two things if you see them in a multiple choice situation. All right. Exception number 2, values that create an even root of a negative number. So you know, like you can't take the square root of negative 4 because square root means what number times itself. And so to get a negative, you have to do a positive times a negative. So you can't do square roots of negatives without getting imaginary numbers, and we don't include imaginary in the domain of our function. So when you have a square root or a fourth root or a sixth root, any even root, then you're going to take the guts of that root, equal it to 0, figure out what value that is. And then we need things that are bigger than that. So you could actually, when you're doing this, if you wanted to say we need to be bigger than or equal to 0, then when you get done, you already have your little domain restriction. So we take the guts, say we need it to be 0 or bigger, do whatever needs to be done to solve it, and then you get your restriction. And again, there's two ways to write it. Set notation says the set of x's such that x is greater than or equal to -1. Or in interval notation, you can say include -1 and go all the way up to infinity. All right, the other one is a log, and again, we're going to talk more about logs in, I believe it's chapter 3. So for right now, you won't see any of those, but it is a domain restriction, so we went ahead and included it here. We want to exclude x's that are going to make you take a logarithm of a non-positive number. So in that case, you want the guts to be 0 or bigger again. And so in this case, actually bigger than 0, not 0 or bigger, because you can't have 0, my fault. So we want x to be greater than 0. So these are the two ways that you'll write that. And again, we'll talk more in depth about that one when we get to chapter 3. Okay, so going back to, we only have 3 exceptions. Just to drive that point home, domain of a polynomial is always going to be -infinity to infinity. Same thing with exponential. If it's a polynomial or an exponential, we know it's -infinity to infinity. Okay? All right, so we want to find the domain of some functions. So first of all, if I just give you a set of ordered pairs, the domain is the x values. So we just write the x's. I prefer in numerical order, but as long as you list them all, you're good. All right, if I give you something that looks like this, your thought is, does it fit one of the 2 restrictions? Does it have a variable in the denominator? Does it have a variable under a root? In this case, yes, we have a variable in the denominator. So take your denominator, set it equal to 0, solve, and we get x is -5. Well, so our domain is any number except for -5. And again, these are the 2 ways of writing it. The set of x's such that x is not -5, or go from -infinity to -5, and then from -5 to infinity. So that just excludes the -5. All right, next option. We have number 9, and my numbering picked up where we left off on Friday, by the way. All right, so here, do you have one of the restrictions? Do you have a variable in the denominator? Do you have a variable under an even root? Yes, we have a variable under a square root. So if we take this and we say that we need the guts to be 0 or bigger, and then we solve, remember that when you divide by a negative, that inequality symbol flips over. So now we're going to have, we want x's such that x is less than or equal to 4/3. And back over here, just in case you need it, I subtracted 4 divided by -3. That's where the 4/3 came from. And then if you want to write it in interval notation, we're talking less than, so we start at -infinity and we go up to 4/3. All right, number 10, this is a polynomial. It does not have the 2 restrictions that we're looking for right now. It does not have a variable in the denominator. It does not have a variable under the radical. So there's no thinking involved. The domain is all real numbers. All right, our next example makes us think about putting some things together. And that's going to happen on your assignment. So you've got to think about what's going on. So here, we actually include both of those restrictions. There's a variable in the denominator, and there's a variable under the radical. All right, so to start with, we are under the radical. So we want to be greater than or equal to 0, right? Okay, well, first of all, I just took the jump that was in that square root, that x squared minus 14, and I solved. And I figured out that 4 and -4 are going to cause us problems. All right, well, the thing is, I'll explain what this means in a minute. You don't have to do that, but I'll explain what it means. So thinking about it logically, if we are under the radical, we would need to be 4 or bigger, or -4 or bigger in the negative direction, so actually less than -4. Because it's in the denominator, we can't use the 4 and -4 because those would give us 0, and that's not okay because it's in the denominator. So that's why I have this. We want to be less than -4 or greater than 4. In an interval notation, that looks like this. We're just excluding everything between -4 and 4, and include -4 and 4. All right, so what's going on here? This is, let's try it and see what happens. We know we're dealing with numbers on either side of 4 and -4. So you like pick a number smaller than -4. So say -6. If you plug in -6, that's going to be 36 minus 16. That's a positive, so that's good. We like those numbers. If you choose -4, you get 0. So -4 is a no-no because you can't have 0 in the denominator. Between -4 and 4, just pick a number in there. You could pick 1, you could pick 2, you could pick -3. I picked a 0. So 0 squared is 0. Minus 16 gives me a negative. The square root of a negative is a no-no, so the numbers in there are a no. If you plug in a 4, again you get 4 squared is 16, minus 16 is 0. Square root of 0 is 0. Can't divide by 0. So 4 is a no. And then something bigger than 4. So you could have picked 10, a million. I picked 6. So again, if you plug in a 6, 6 squared is 36, minus 16 gives you 20, a positive number, so it's good. So we know the numbers bigger than 4 and smaller than -4 are the numbers that are good. Again, like, you don't have to do this. This is if you need to check all of your possibilities. Most of us can kind of logically think about what's happening. All right, so the next thing is the difference quotient, which is really just, can you evaluate a function for something ugly? And it's leading you into being able to do limits in calculus. All right, so we have the difference quotient is this. H is not 0, obviously, because you can't divide by 0. So as long as you're not trying to say H is 0, the difference quotient works. So the way the problem is going to look is it's going to say, here's a function. Find the difference quotient. And it may say find the difference quotient, and it may just say find this. It may give it to you. All right, so you're going to take this function and do this work. So we're going to take f of x plus h. So take the function and replace the x's with x plus h. So that's this part. Then we have minus f of x, so just minus the function. So making sure we know what's going on. We did this here, and we did this here, and then it's over h, and there's a minus on. So those pieces just are also there. Alright, so then you have to do the work to clean all of that up. So if we do x plus h squared, we get x squared plus 2xh plus h squared. You can go over to the side and distribute it out and see that that's how this comes about. We distribute the 4, so we have 4x plus 4h plus 7. Minus has to distribute, so then you have minus x squared minus 4x minus 7. Alright, so then we just combine our like terms. So x squared minus x squared cancels. 4x minus 4x cancels. 7 minus 7 cancels. So you notice how all of your pieces are the ones with h's in it? Well, that's supposed to happen. So you can factor that h out. So take an h out of all of these and it looks like this. And it divides off with the denominator and you just have this simple piece left. Now again, that's leading you into doing work to be able to find limits and derivatives and things like that in calculus right now. We're just making sure you can do the algebra involved. So if you're asked to find the difference quotient, you don't need to know where it's going, what it's doing. We're just finding the difference quotient. Alright, so on Friday, you got this little summary of function terminology. Glue that in, read through it. It's just reminding you what some of the big definitions are. So at this point, we should understand the definition of a function. We should know about function notation. We should understand domain and range. And we should understand that implied domain is if we're not given a context and we don't have domain restrictions, then it's going to be all real numbers. Alright, we should have time in class today to start section 1.5, so I want to go ahead and do that. Your assignment is only over section 1.4, but starting section 1.5, analyzing graphs. We're just going to do the can you find the zeros of a function today. So keep in mind that zeros are also called x-intercepts. They're the x values that make your function 0. Okay, so all that means is that if you're asked to find the zeros, you want to know the x-intercept. You want to know where does it touch the x-axis. Where is y, 0? So if you replace f of x, which is really just y, with 0, and then you just have an equation to solve. So if you think about this one, it's a trinomial, quadratic trinomial, exponents of 2, 3 terms, quadratic trinomial. We should be able to factor, just good old-fashioned guess and check. So we know that 3x times x gives us 3x squared. We know that 2 times 8 is 16. We know we need one negative, one positive, because it's negative 16, so I chose negative here, positive here. Checking to make sure that we get 22 in the middle. 3x times 8 is 24. Negative 2 times x is negative 2x. That gives us the 22 in the middle. Alright, so now you have it factored. You can use the zero product property to set those factors equal to 0 and solve. And you get 2/3 and negative 8 as the zeros of the function. If you need help with factoring, let me know. You can Google, there are a million options on factoring videos that are helpful. Alright, number 2. Again, your function is given. You want to equal it to 0, so change f of x to 0, so it looks like this. Now you need to get that denominator off, so we multiply both sides by 4x, which really just makes that 4x disappear. So now we again have a quadratic trinomial, so we should be able to guess and check. Set your factors equal to 0 and solve. Keep in mind that you multiplied and you got an excluded value of 0. All that means is that if you get 0 as a solution, it's not an actual solution, because what's happening here is that's a restriction in your domain, and it's going to be something weird with your graph, like an asymptote or a hole, and that's something we'll discuss later. For right now, you just need to, if you have to multiply by a variable to get it off of the denominator, keep in mind that it's an excluded value that you can't use as a solution if you happen to get it. It's not that often that you will. Alright, so I think that's as far as we're going to get today, and I'm going to give the end of class to work on the assignment over section 1.4. If you have questions about any of the notes, let me know. If you have questions about your homework, let me know.